Hello again. This is section 8.2, circles and triangles in neutral geometry. So we've already been talking about circles, and now we're talking about triangles as well. And we're still in neutral geometry. This is the section we would have covered Friday, and I'm recording this on Tuesday. All right. So you can say this with me if you want. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. Okay. All right. Ready to dive in? Let's do it. A circle that contains all three vertices of the triangle ABC is said to circumscribe the triangle. The circle is called the circumcircle, and its center is called the circumcenter. If a triangle has a circumcircle, we say the triangle can be circumscribed. Can be circumscribed. Okay. A triangle can be circumscribed if and only if the perpendicular bisectors of the three sides of the triangle are congruent. If concurrent, concurrent. Remember, concurrent means they all intersect at the same spot. So if a triangle can be circumscribed, then the circumcenter and circumcircle are unique. All right. So we're going to need to use theorem 437, pointwise characterization of perpendicular bisectors. So first, if and only if. So let's pretend that a triangle ABC, let's pick a triangle ABC that that is circumscribed. So there's A, there's B, there's C. Okay. So then if we look at the perpendicular, different colors here, otherwise it's going to get messy. Let's draw some perpendicular bisectors. So there and there and there. So those are the same, those are the same, those are the same. And then let's do a different color for the point. Point is there. Oh. Okay. So if, let's see. So our theorem goes both ways. And first we say if it's circumscribed, then the perpendiculars bisectors are concurrent. And if it's circumscribed, circumcenter and circumcircle are unique. Okay, so call this line L, and call this line M, call this line N. Okay, so first, why do L and N intersect? Well, we can do that by contradiction. So assume L is parallel to, say, N. Well, if L is parallel to N, well, L happens to be perpendicular to BC. Therefore, let's see, therefore, sorry, I got a little ahead of myself. I was doing the wrong direction. So we don't need to do by contradiction here. We can just look at OA and OB and OC and say, well, if you look at, you've got this perpendicular bisector there. And so we know that, I'm gonna use red for the red size. So we know that OA, OC, and OB equals OB equals OC by our hypothesis. In that case, the O is on the perpendicular bisector of AC, if and only if OA equals OC by the pointwise characterization of perpendicular bisectors. Therefore, N is a perpendicular bisector of AC, and L is a perpendicular bisector of BC, and M is a perpendicular bisector of AB. So that way it's done. So now do it the other way. So now I'm just going to erase this and do the next proof. Okay. So now assume it the other way. Assume that I have a triangle and I have perpendicular bisectors. So perpendicular bisectors for the triangle. So that's the same, that's the same, that's the same. And these are all right angles. Let's call this A and B and C. Call this L and M and N. Assume they are all concurrent right here. Well, in that case, let's draw some new lines. So call this point like P there, okay. Actually, let's not call it P, let's call it O. All right, so draw from O to C, O to A, and O to B. Well, then, in that case, we have side angle side here that what's going to be the best way to do this? Basically like yellow triangle congruent to yellow triangle, and blue triangle congruent to blue triangle, and purple triangle congruent to purple triangle. So we have these congruencies, which makes that means that this is congruent to that, congruent to that. Hence, they're all the same distance, and circles are distances. Therefore, they're all part of the same circle. The end. Okay. Now, let's see. So now here's our big theorem for this section. The Euclidean parallel postulate is equivalent to the assertion that every triangle can be circumscribed. Okay, and then Venema breaks this theorem into, like, there's two directions for this theorem because it's equivalent to means it's got an if and only if. So then he breaks it. Really, he could have made these lemmas, but they're so big that they might as well be theorems. So the proof that EPP implies every triangle can be circumscribed. Well, then assume I have a triangle ABC. And I'm assuming the EPP holds. So then I'm going to take my triangle and I'm going to perpendicularly bisect AB. And I'm going to perpendicularly bisect, I think I might want to bisect, yeah, I'll bisect at least two sides. Call this line L, call this line M. Okay. Now, first, L intersects M. Assume by, like, we prove this by contradiction. So assume L is parallel to M? Well, we know that L is perpendicular to AB, and M is perpendicular to AC. So that means that AB is either equal to or parallel to AC, because we're in Euclidean land. But this is absurd because it's a triangle. Then AB equals AC, or AB is parallel to AC. They can't be parallel because they share a point, and they can't be equal because it's a triangle. So absurd. So they must touch. So call that point where they intersect O. Then, if I draw the lines from there to there, actually, let's do that in a different color because it's going to get messy. All of our triangles get messy these days because there's so much going on. All right, there we go. So I've got perpendicularly bisected by design. That's congruent to itself. Therefore, this is congruent to that. And then the same principle over here with these two triangles tells me that's congruent to there. But then I have three lengths that are all the same. That means that A, B, C are part of the same circle because circles are just distance. Okay, so then that's done. So then the corollary is that in Euclidean geometry, the three perpendicular bisections of the sides of any triangle are congruent, immediate circumcenter of the triangle. Okay, if the EPP fails, then there exists a triangle that cannot be circumscribed. So we're kind of doing the contrapositive. And so for this one, I'm just going to draw you the picture, but it relies on theorems that we skipped because we skipped the hyperbolic section. So imagine we're in hyperbolic land. So if the EPP fails, we have those theorems that basically say you have to be hyperbolic then. So then you have, I'm just going to grossly exaggerate that. Okay. Then I'm going to do that. And then I'm going to perpendicularly bisect this line. Call this A, B, C, D. And I'm going to perpendicularly bisect here. Call that point M. It's going to intersect there at N. And then make it so that that's the same, and then make this point be the same distance, E. Okay, so then if I make, draw the line from D to E, draw the line from E to C, then I know that D, E, C are not collinear because D and C are collinear. And so then if I draw, if I perpendicularly bisect again, I've got another Sachery quadrilateral right here, which means that's going to be perpendicular. I've got another Sachery quadrilateral on the right side, which means that's going to be perpendicular. And so that makes this guy, what color should we do? Purple? It makes this one right here a triangle, a hyperbolic triangle. And yet, look at how this is a perpendicular bisector here. That's a perpendicular bisector there. That's a perpendicular bisector there. They are all parallel to each other. And so they're never going to intersect. Wherever they intersect would be the center of the circle, but they never intersect. So there's no circle. Okay. So moving on. If ABC is a triangle and we have a circle COR, it's inscribed, called the inscribed circle for ABC if each segment of the triangle is tangent to COR. The center of the inscribed circle is called the incenter of the triangle, so incenter. Okay, so if you have a triangle, and then you can draw the circle tangent to everything, that is the incenter. So this is, remember, we're in neutral geometry, so we have a theorem that says every triangle has unique inscribed circle. The bisectors of the interior angles of any triangle are concurrent at the incenter. Okay, so the way to do this is to bisect all three angles. So if we bisect all three angles, so bisect there, and bisect there. Okay, well, if I bisected here, so then I know that my bisection crosses there, right? And because of the crossbar theorem. And then I know that this bisection crosses here by the crossbar theorem. So then at least call, I should name this, so A, B, and C. So then if I bisected A and bisected B, I know they will intersect. Call that intersection O. I haven't proved that O is where the OC is also there, but I created that bisection. So then by bisecting the angle, then I want to claim, so call this point D, call this point E, call that point F. So then OD, let's say OF right there. Well, let's not bisect the third angle yet. Let's claim that later. So